Hello, this is Eric from UNC Charlotte. MapReduce is the programming model that is easy to understand and use. This video introduces the MapReduceMPI implementation of the programming model, which leverages MPI for communications. We illustrate the API with a simple running example. MapReduceMPI is an open-source C++ library written by scientists from Sandia National Labs. It provides MapReduce functionalities within MPI applications, so the calls to the library can be mixed in with MPI calls. The library performs calculation in core, but it transparently operates in an out-of-core mode if there is not enough memory on the computing nodes. MapReduceMPI has a fairly simple API. Its summary fits in a single screen, and most of the functions of the interface apply to a MapReduce object. A MapReduce object stores key-value pairs in most cases, for instance, when used as the output of a map or reduce phase, but it can also contain key multi-value, usually used as the input of a reduce phase. While the interface is a C++ interface, most of the data is being passed as pointer plus size. The typical workflow of a MapReduceMPI application starts with the execution of a call to map. It creates map tasks and produces key-value pairs. The map tasks are parameterized out of numbers, files, or other key-value pairs. Eventually, the application calls aggregate, which redistributes the key-value pairs between the nodes of the distributed memory machine, so as to bring the key-value pairs with identical keys on a unique node. Convert prepares the key-value pairs for reduction by grouping key-value pairs with identical key into a single key multi-value pair. Reduce creates a task for each key multi-value pair. That task can inspect the multiple values for that key and produce new key-value pairs. There are 5 variants of map in MapReduceMPI, which create map tasks in different ways. The simplest variant creates n map tasks identified by a single integer from 0 to nmap-1. The second parameter is a pointer to a function to be executed by each map task. That function takes a task ID, a pointer to a key-value object to use as an output, and a pointer to a user-defined context. The third parameter of map is a pointer to that user-defined context. Map and reduce user-defined functions receive a key-value object, which is mostly used by calling add on it. It creates a new key-value pair by copying it into the MapReduce object. Both the key and the value are represented using pointer plus size. The key is the buffer of a particular length. Similarly, the value is also a buffer of a particular length. Scan can be used to inspect the content of a MapReduce object. There are 2 variants for either key-value pairs or key multi-value pairs. This scan function will take a callback function to be called on each key-value pair and a context. The callback function takes both the key and the value as pointer plus size arguments, and it also takes a context. We use the Monte Carlo approximation of pi as an example application. The method draws n uniformly random points in the unit square and counts c, the number of points within the unit circle. The ratio of c to n is a good approximation of pi over 4. We can generate map tasks that draw an arbitrary number of points and count how many are within the unit circle and how many are not. These are pushed as key-value pairs with a dummy key. A reducer counts the total number of points within and outside of the unit circle across all map tasks, and that information is enough to derive a good approximation of pi. We show first how the map tasks are created, and we will show the reduction later. MapReduceMPI requires initializing and finalizing MPI. The application parses the command line parameters to extract the number of map tasks and the number of points per map task. After creating a MapReduce object, it calls map to create the requested number of map tasks and each of these tasks will execute the 1Pi function. The number of points per map task is passed as context. Once that map phase is executed, a call to scan is used to print out all the key-value pairs that are stored in the MapReduce object. The 1Pi function takes three parameters: a map task ID, a key-value object to use as an output, and a context. 1Pi uses the context to know how many points to draw. Then it generates the state of a random number generator by using its map task ID. This is important to ensure that the different map tasks uses independent random number generators. 1Pi then draws random points and counts how many are within the unit circle and how many are not. Finally, the map task creates a single key-value pair. The key is a single integer and is passed by giving the address of that integer and indicating how many bytes it is. The value is composed of two 64-bit integers. Because they are stored in a stud pair, they are contiguous in memory, and they can be passed directly by giving the address of the pair and its size. PrintKVPair is a simple utility function which assumes that the key is composed of a number of variables of the same type key, and the value is also composed of some number of variables of the same type value. It prints the key-value pair in the tuple notation. When running the code, we can see that it created the requested number of map tasks. The different map tasks used different random seeds. We can also see when running the code on multiple MPI processes that the execution is actually distributed, and the key-value pairs are stored on the MPI ranks that created them. Before reducing, we need to group together the tuples with identical keys. This is accomplished by two functions. Aggregate brings all the key-value pairs with the same key on the same MPI rank. You can control the mapping of keys to MPI ranks by passing a custom hashing function, but in most cases you can use the default one by passing null. Convert will string together all the values associated with the key and transform the key value into a key multi-value. Collate is a convenience function that executes both aggregate and then convert. Calling reduce on a MapReduce object starts a reduce phase. For each key, the MyReduce function will be called and it will be passed the local context. MyReduce takes the key, the values, and a key value store to use as an output, and also a context. As usual, the key is provided as pointer plus size. The values are all passed in a single buffer. The values start at multi-value, and there are n values in total. The size of these values are passed in the value bytes array. In other words, the first value is stored at multi-value, and it is value bytes of 0 bytes long. The second value is from value byte 0 and runs for the next value bytes 1 byte. In rare cases, there may be more values than can be stored in a MapReduceMPI page. In such a case, the multi-values will be null, and we will cover how to handle that case a little bit later. In the application, the main function calls collate to prepare for the reduce phase. Then it calls reduce, which runs PySum on every key. Finally, it will print the result by calling printPy on the key-value pair produced by reduce. The values that come to the PySum function are pairs of integers which count the number of points in the circle and the number of points out of it. PySum iterates over all the values simply by summing each component of the pair. Note that it maintains a base pointer to point at the beginning of the next value. Finally, it pushes the results as a key-value pair. The printPy function works pretty much as you would expect. MapReduceMPI manages its data in pages of 64 MB by default. If the data to reduce is larger than a page, then it splits the data in multiple pages which may be stored in the file system. Programmatically, you can tell that the reduction is composed of multiple pages because the multi-value is a null pointer. We can run the previous Monte Carlo code with a very high number of map tasks to see that it eventually segfaults because multi-value is null. When there are multiple pages, the underlying MapReduce object is passed as the value bytes array. That MapReduce object provides two functions to iterate over all the multi-values. The first one is multi-value blocks. It returns the total size of the multi-values and writes the number of pages to the integer passed as a parameter. The second function is multi-value block, which loads the page passed as the first parameter. It returns the number of values in that page and writes multi-value and value sizes to the addresses passed as a parameter. In this paged implementation of PySum, the logic to process a page has been pushed to a lambda function. The code checks whether there are multiple pages by checking whether multi-value is null. If there is a single page, it processes it naturally. If there are multiple pages, it extracts a pointer to the MapReduce object. It calls multi-value blocks, which writes the number of pages to the parameter nbblocks. Then it loads the pages one by one with multi-value block and calls the lambda function to process that page. We can run the code to see that it correctly processes the different pages. A common performance problem in MapReduce is that reductions cause network communications. That network communication happens in MapReduceMPI during the call to collate. It is actually a call to both aggregate and convert. In MapReduceMPI, one can reduce locally on each MPI process before reducing globally. To achieve that, one calls convert without calling aggregate. This causes each process to independently create key multivalue and enables reducing locally. Finally, a call to collate and reduce enables performing the global reduction. We can see that running the optimized code yields a smaller runtime than the first code. This performance improvement is due to the reduction in communications. MapReduceMPI enables using MapReduce semantic inside of an MPI application. The map function executes a callback for each map task. Aggregate and convert are used to prepare the MapReduce objects before reduction. The reduce function creates a reduce task for each key on an MPI process. The values are usually stringed together, but the values can be split on multiple pages that need to be loaded explicitly. We only covered in this video the basics of MapReduceMPI. For instance, there are many more map variants that enables creating tasks from files or from existing key-value pairs.